last topic in section 9.1 is how to test a population correlation coefficient. So, what we've been calculating so far is the sample correlation coefficient, where you have a small set of data that is pulled from a larger population. When you calculate that R, you're going to want to know if there's enough evidence to decide that the population correlation coefficient, which we denote by the Greek letter rho, looks pretty much just like a P, whether or not that's significant. In other words, based on a few pairs of data, your sample, can you make an inference about the population of all such data pairs? In correlation studies, the small percentage of times when you decided that the correlation is significant when it really isn't is called the level of significance, which we denote by the Greek letter alpha. It's typically set at alpha equal to 0.01 or 0.05. And here's what those mean. At a level of significance of 0.05, you'll probably decide that the correlation is significant when it really isn't 5% of the time. So you're going to be wrong 5% of the time, but 95% of the time, you'll make that decision correctly. At a level of 0.01, you'll probably decide that the correlation is significant when it really isn't only 1% of the time. So 99% of the time, you get it right. But using the lowest level of significance to guarantee the fewest errors does have disadvantages. You may fail to identify some significant correlations that just don't meet such a high threshold. So it's kind of a balance. In Appendix B of your textbook, you're going to find Table 11, which we use to figure this out. In general, the fewer number of data pairs you need, the stronger evidence you have to conclude that your correlation coefficient is significant. So here are the steps for using Table 11, and we'll go through these steps by doing Example 6 in your book. Example 6 uses the data from Example 3 that we used on Old Faithful, the world's most famous geyser. So based on the number of data points in the sample, the correlation coefficient, and wanting a level of significance of 0.05, is our correlation coefficient significant? So first of all, you would have to go back to the original data set. And in the original data set, there were 25 pairs of data. And that's our value n. Our alpha, our level of significance that we're looking for, is 0.05. So the third thing we have to do is find our critical value using Table 11. So next you would need to go to Table 11. Our sample size was 25. So under the n column, I'm going to find the row that corresponds to 25 data points. Now, as you can see at the top, these are labeled with their level of significance. If you want 0.05, you use the number in the second column as your critical value. If you want a level of significance of 0.01, you use the number in the third column. So we were asked to use alpha equal to 0.05, which gives us a critical value of 0.396. Step 4 says if the absolute value of R is greater than your critical value. So you would have had to have calculated R like we did using Excel. And we're going to round it to 3 decimal points simply because that's what this table is set up for. So when we used Excel to get R for this data set, we got 0.979. So now we need to check and see if the absolute value of R, which is the absolute value of 0.979, is that, and I'm going to put a question mark over this greater than sign because I'm checking, is that greater than our critical value 0.396? Now, these vertical bars are the absolute value symbol, and all they mean is take whatever is inside and make it positive. So basically, we don't need to worry about whether this is a positive or a negative correlation when we're determining significance. We just make whatever our correlation was a positive number. So the absolute value of 0.979 is just that number. It's already positive, so it stays positive. And that is, in fact, greater than 0.396. And because of that, then we can conclude that the population correlation would be significant. So, in other words, this is a useful sample. I'm just going to write yes, the population correlation is significant. We have enough evidence at the 5% level of significance to conclude, and again, we have to do this in the context of the original claim. In other words, go back to what this actually means. There is a significant linear correlation between the duration of Old Faithful's eruptions and the time between them. The 5% level of significance, that comes from back over here. When we use alpha at 0.05, remember that said that we'll decide something is significant when it really isn't 5% of the time. So that's called a 5% level of significance. Okay, so this helps you interpret your R value and determine if it's going to be representative of the entire population or not. But a few words of caution, and I made this required reading for this section, so I'm not going to go through and read the whole thing to you. But it's important that just because you get a strong correlation between two variables, do not automatically assume that one of them caused something to happen with the other one. You have to do more in-depth study if you want to determine if changing one variable is the direct cause of changes in another. So, possibilities to consider. So, once you get this strong correlation, you want to think about, is there a direct cause and effect relationship? Does X cause Y? So, in other words, if X is the amount of sleep that I get, cause Y, the grade on my math test the next day, is there a relationship there? Does me getting more sleep cause me to do better on the test? For some people, maybe yes. For some people, maybe not. Is there a reverse cause and effect relationship? Is it actually the other way around? So, does me taking the math test cause me to get less sleep the night before or more sleep? Is it possible that the relationship between the variables could be caused by a third variable, or perhaps a combination of several other variables? Me doing well on my math test, sleep might be one factor, but how much studying I did is certainly another. And is it possible that the relationship between two variables might just totally be a coincidence? So that is also a possibility. So again, for more details on this, please do the reading from this section on page 480.